Yeah.
So hello everyone, my name is Mayank and I am presenting my paper on the application of mean field homogenization for transversely isotropic matrix. I'm a MTech student at IIT Kharagpur. For my presentation, what we have done in our research is that since composite material are a new thing in the market and a lot of research has not been done in this field, what we have done is to find out the analytical methods from which we can find out the properties of the composite material. As you know that the composite materials are a mixture of more than two materials, so it is very difficult to find out the properties of the heterogeneous material. Right now, the method which are available in the field are a finite element method, but they are very time consuming. So we have predicted the capability of a Mori-Tanaka method, which is used to find out the properties of composite material. So Mori-Tanaka method is perfectly fine for isotropic matrix, but when the matrix become transversely isotropic, and then in that case we want to uh, test the accuracy of it. So in this paper we are going to present the same. So the theory behind is that the stress strain relationship in the linear elastic region is given by sigma ij is equal to CijKL into epsilon KL. So this epsilon is the elastic strain and sigma is the uh, stress, and the C is the stiffness matrix of the material. The first development was done by Shelby in 1957, where he find out a method to find out the effective properties of the composite material by SLB tensor. So SLB tensor relates the strain in any fiber to the eigenstrain. So eigenstrain is basically any inclusion when it is not constrained from any surrounding, and the strain developed in it when it is not constrained from any surrounding. So let's say, let me. Let's say this is a matrix material and this is a fiber. So if I take the fiber out from the matrix material and then apply an external strain, so it will either it will deform to a certain extent. That strain is known as the eigenstrain. So SLB tensor relates that eigenstrain to the constraint strain. So there are some expression for SLB tensor for isotropic material, but not many literatures have described the SLB tensor for anisotropic medium, because they are very difficult to calculate. And I think SLB tensor is the best method to find out the overall properties of the composite material. So there are few literatures we have who have tried to calculate the Shelby tensor for a transversely isotropic medium, and we want to find out we want to test the accuracy of. So for Mori-Tanaka formulation, so SLB tensor was applicable for that when there is a single inclusion and the inclusion is in a matrix. But as you know that the one fiber also affect the properties of the other fibers. So let's say there is some stress in one fiber, that stress will also affect the stress in the other fiber. So Mori Tanaka was the first who related these stresses and the strains uh, in the individual fiber and also to the overall fibers. So strain concentration tensor basically relates the strain in some. Uh, can you
I request the other candidates to mute your mics, please.
Okay. So the strain concentration tensor is basically the strain which relates the strain in the fiber to the applied strain. So if there is a single inclusion and the matrix, then in that case, that strain concentration tensor is known as dilute strain concentration tensor. So for any individual fiber, it is given by this expression, where this I is the identity matrix, S is the Shelby tensor, Cm is the stiffness matrix of the matrix material, and then C alpha is the stiffness matrix of the individual fiber, and this again Cm is the stiffness matrix of the matrix. But if I want to study the effect of other fibers on that particular fiber, then this is given by strain concentration tensor. So strain concentration tensor is given by this. So this AM is again the dilute concentration tensor, and then VM is the volume fraction of the matrix. I is the identity matrix, and then V beta, this is the volume fraction of that particular fiber for which we are calculating the strain concentration tensor, and then again in this AM is the dilute strain concentration tensor. So in this way we can find out the effect of the other inclusion on that particular inclusion also. And then again, so so the strain in any particular inclusion is given by then this strain concentration tensor, and this epsilon naught is the externally applied strain. So now we have the strain in that particular fiber, so we can calculate the stress in that fiber. And this is for the fibers. And to calculate the strain concentration tensor for the matrix, we can calculate it this way. And again, the same way, we have the strain in the matrix and then stress in the matrix by this method. So finally, when we have all the formulas for uh, all the things, we can calculate the effective stiffness matrix of the overall composite, which is given by this formula. So this Cm is the effectiveness matrix of the matrix material. This V alpha is the volume fraction of that fiber or inclusion, and this C alpha is the effectiveness matrix of the inclusion, and this Cm is the effectiveness matrix of the matrix, and this E alpha is the strain concentration tensor. So now to test the validity of this method when it is applied to transversely isotropic matrix, we have developed a finite element model which were generated with the help of a MATLAB code. So basically, we have tested this method on prolate ellipsoid. So prolate ellipsoid is basically when a ellipse is rotated about its major axis. So this is prolate ellipsoid, and this is oblate ellipsoid. So we have done our experiment or finite element modeling or for the prolate ellipsoids only. So we have tested it on abacus, and we have done the analysis for two aspect ratios, that is 3 and 10. So aspect ratio is basically A by B. So A is the semi major axis of the ellipsoid, and B is the semi minor axis of the ellipsoid. So these are the finite element models we have generated. So these are the fibers with aspect ratio 3, and number of fibers in this model were kept at 40, and this model is for aspect ratio 10, and number of fibers in this model were kept 20. This is because there was difficulty in meshing. If we have kept the number of fibers in this model as 40, that's why we have reduced the number of fibers in this model.
Yeah, Mayank, I am interrupting you, your presentation. You just make it fast and go to your conclusion slide.
Okay. So for results, we can see so the C11 and C22 of the composite. So C11 and C22 of the composite, we can see there is a clear match between the Fe results and the Mori-Tanaka formulation, and there is an exact match. There is a very close match for average stresses in the fiber and the matrix, and the average stresses in the S22 for there is some gap at higher aspect ratio for fiber and the matrix. So we can conclude from this that the Fe results and Mori-Tanaka results match for a lower aspect ratios. For aspect ratio of 10, which is higher aspect ratio, we can clearly see that there is a deviation when we go at a higher modulus mismatch. So this x-axis is basically Young's modulus of the fiber, and this is the C11 of the composite. Similarly, this axis is a Young's modulus of the fiber, Young's modulus of the fiber, Young's modulus of the fiber. So we can see that as we go from lower to higher modulus mismatch between the fiber and the matrix, we can see there is a clear deviation. And for the similar cases of S11 in the fiber, stresses, and also the effective properties of the overall composite. So we can conclude from this result that the Fe results and Mori-Tanaka results deviate at higher aspect ratio of the fiber. So we can conclude from our study that the Mori-Tanaka is an excellent mean field homogenization scheme for a transversely isotropic matrix when all the fibers are aligned in the direction of the anisotropy of the matrix. but it is not a good method when it is not a good method when the modulus mismatch between the fiber and the matrix is high, and also it poorly predicts the results when the matrix anisotropic axis from that of the fibers alignment axis. So fibers are aligned in the x direction. That means the semi-major axis of the fibers is in the x direction. But if we change the semi-major axis of the fibers in the y direction, then the Mori-Tanaka method does not predict the results to that accuracy. So that is all from our study. If you have any question, you can ask.